Hello, everyone. My name is Paula Perez. I am the product manager of ACTINIS, which I will present in this workshop. A short outline of my talk. So I will shortly present CAMECA, and then I will introduce the dynamic SIMS technique for those that do not know it. And after that, I will speak about ACTINIS, its key features, and show a few applications of this instrument at the end. So CAMECA is a supplier of microanalytical instrumentation, which is mainly based on three main techniques: electron probe microanalyzers, EPMA, secondary ion mass spectrometry, SIMS, and atom probe tomography. So this talk will be mainly focused on the SIMS technique. So EPMA and SIMS are complementary techniques for the analysis of radioactive samples. So just I wanted to recall you that we have a specialized EPMA instrument, the SCAFIA, which is a shielded electron probe microanalyzer dedicated to the analysis of radioactive samples. And we have the new ACTINIS that I will present in this workshop, which is a shielded SIMS instrument also for the analysis of highly radioactive samples. So let me introduce first the dynamic SIMS technique. So when a solid sample is bombarded by a focused primary ion beam, particles are emitted from the sample following collision cascades. Among the particles that are emitted, a given fraction is ionized. So we'll have less than 1%, depends on the species, but we'll have a fraction of ions coming out. And these ions will be collected and analyzed in the mass spectrometer. We call these ions coming from the sample the secondary ions. This is what is interesting for us because these ions are characteristic of the composition of the analyzed area. So SIMS allows in situ local analysis of any solid material. The only constraint is that it needs to be a flat surface. Of course, this material needs to be compatible with high vacuum. So SIMS reveals both elemental and isotopic composition, and for quasi all species of the periodic table, from hydrogen to uranium and beyond. Dynamic SIMS is a destructive technique by its nature. We are sputtering the sample using high-dose ion bombardment, and we get information, elemental and isotopic, from a depth range which can vary from a few nanometers to tens of micrometers. It is also known for its very high sensitivity. You can see here a schematics of the CAMECA IMS7F design, which is one versatile SIMS instrument. This instrument, as you can see here, has a primary ion column with two primary ion sources, cesium and oxygen, depending on the species we want to analyze. So there is a continuous primary ion bombardment and a continuous secondary ion extraction using high electrical field. The ions that come out of the sample, the secondary ions, will be collected here and then analyzed, go through the mass spectrometer, which is based on the coupling of an electrostatic sector and a magnetic sector. Magnetic sector will separate the ions according to their mass. The detection will then record the ion intensities. In this type of SIMS instrument, we are working in monocollection mode, which means that elements are acquired one by one by scanning the magnetic field. The ion intensities are recorded using two different kinds of detectors, an electron multiplier or a Faraday cap. So to summarize, we are using a continuous primary ion beam bombardment continuous ion beam extraction. This provides high throughput and high sensitivity for all species. Because of the design based on a high electrical field, we guarantee high transmission, which is very important in order to achieve low detection limits. And the combination of the electrostatic sector with the magnetic sector provides high performance in terms of high mass resolution and high abundance sensitivity. I will show an example later on of an application for those who are not familiar with the high abundance sensitivity. So the typical dynamic SIMS outputs. So dynamic SIMS using a magnetic sector mass spectrometer is well adapted for analysis of inorganic materials. Both elemental and isotopic information can be obtained. It is ideal for depth profiling analysis. When low detection limits are needed, we can achieve from ppm to sub-ppm level for all elements, including the light elements such as hydrogen, carbon, and oxygen. It is also well adapted for when the depth to be sampled is large. So we can go up to tens of nanometers, micrometers, as I said before, but we can also analyze a shallow depth range of few nanometers. It is also one very typical output is ion imaging, so mapping. As we can see here in this example, we can see the mapping of uranium in a cell culture. So we can achieve both images with high mass resolution and at high sensitivity, so with a lot of counts, so with good statistics. We can also perform high precision isotopic ratio measurements for any species. We can see here an example of an isotopic ratio measured in an oxide sample. So we can see here that dynamic SIMS can be applied to many different types of fields. We can see the example on the left is a phosphorus depth profiling in silicon, so a lot of applications in microelectronics. In the middle, we can see an application in biology, and on the right side, we can see an application in geology, geochemistry. So a very broad range of applications. It's also known for its high throughput. So one analysis can be as short as few minutes. It can also be longer, mainly for the ion imaging. But in general, we can have a lot of high throughput and high productivity. So to summarize, dynamic SIMS is a highly sensitive surface analysis technique. It is a destructive technique. The sample is sputtered. Quasi all elements can be analyzed, from hydrogen to uranium and beyond. We can, it provides in situ localized microanalysis, both, as we've seen before, depth profiling, imaging, and also 3D volume reconstruction are available. So very high sensitivity with very good detection limits from ppm to ppb level. It is a quantitative technique for low concentrations, below 1%, provided that standards are available with the same matrix composition. The isotopic composition can also be obtained using SIMS with high precision. And we can analyze any vacuum-compatible material. It can be conductive, semiconductive, or insulating, no problem. Sample preparation is rather simple. We need, however, to have a flat, polished sample surface. So let me switch now to ACTINIS. So ACTINIS is a magnetic sector SIMS, which has been designed for the analysis of highly radioactive samples, typically irradiated nuclear fuel. We can see here a 3D view of ACTINIS. So the name ACTINIS is inspired from the Greek actis, which means ray. But it also refers, of course, to actinides that you know very well, so elements which are very important for nuclear applications. So the ACTINIS is based on the CAMECA IMS7F system. We have seen the schematics before in the previous slide. So it offers very good SIMS performance, modern electronics and user interface and user-friendly software. ACTINIS also benefits from the close collaboration between CAMECA and the CEA, Cadarache in France, and from many improvements of the technical design based on experience from the first generation shielded SIMS instrument, which was called IMS6FR. Two were installed worldwide, one in ITU Germany, decommissioned since then, and the 6FR in CA that will be that is being replaced by ACTINIS. So CAMECA has designed biological protections to ensure a safe environment for the operator. So you can see, you may not see, but inside this shielding, this lead shielding, there is a glove box with a manipulator for sample handling that we see here. And so this lead shielding is surrounding the glove box as well as the airlock and the analysis chamber. You can also see that there is a LED window here for visualization of sample handling. You can see here a 3D view of ACTINIS with the electronics. So it includes IP54 racks, which are very specific racks that protect from dirt, dust, drips, and splash. And there is a special cable path that we can see here that avoids having cables on the floor. And here you can see a picture of the first ACTINIS at the CAMECA factory very recently, on September. So this first ACTINIS has been shipped since then to CA Cadarache, and it will replace the 20-year-old shielded IMS6FR. By the way, I knew today that this ACTINIS, we are starting already doing the specifications for this instrument. So there is an ion beam already on the instrument on site at CEA. So here it's a synoptic of ACTINIS. So for those who know the CAMECA IMS7F, you will recognize the SIMS instrument. So there is a primary column with a cesium source here and oxygen source there. I didn't mention before, but the cesium source is mainly used when one wants to analyze electronegative species, for example, hydrogen, carbon, sulfur, chlorine. And the oxygen source will be selected when we want to analyze electropositive species, metals, uranium, boron. You can see, so the ion beam from the source will go through the primary column, and we will bombard the sample, which is here. This is the analysis chamber. This is the introduction system, which is specific to ACTINIS, which is a full security sample system. I will show it later, more in detail. Here we can see the mass spectrometer based on a magnetic sector. And here the detection system, which is a specific detection system inherited from the 7F GO with two Faraday cups, two high-performance Faraday cups, in addition to the electron multiplier. And we can see here the beginning of the glove box, which has a manipulator, and also the lead walled shielding here. The maintenance inside the shielding is very important. It's a critical point because, as you understand, we needed to develop specific tools that allow maintenance inside the shielding. Several ion optical devices have been modified also to allow maintenance, and there have been other adaptations of the physics in order to adapt to the shielded cell. So we see here another picture of the first ACTINIS at the CAMECA factory from another angle. What I wanted to show more in detail, Here you can see there is a model of the glove box with the manipulator. So it was installed in the factory to check the handling and all the maintenance operations in the glove box. You can see here on the front the introduction system. So here it's the analysis chamber, and here the airlock with a door allowing to introduce a sample holder inside the airlock. And then there is a motorized rod that brings the holder from the airlock to the analysis chamber for analysis. When the analysis is finished, the sample holder is brought back with a rod to the airlock. And you can see here the detection system I mentioned before with one electron multiplier and two Faraday cups with state-of-the-art electrometry, which means that there is a low noise level for these Faraday cups and also a very stable baseline. And this, of course, it's very important for high precision isotope ratio measurements. So the maximum sample size that can be analyzed in ACTINIS is 1 inch in diameter and about ½ inch in thickness. You can see here a sketch of the sample holder and the mount being introduced, which is introduced from the top inside the holder. Typically, at least in a CEA, the sample is mounted inside a metallic ring, but it can also be mounted directly in the sample holder. So it is very important, but of course the sample holder handling and also the door of the load lock can be manipulated using the 2-finger manipulator. You can see here a more detailed sketch of the rod inside the introduction system. Here you can see the load lock door. Inside you can see the rod has 2 positioning pins. In fact, what happens is that below the sample holder there are 2 holes. So the sample holder is going to be positioned very precisely on these pins, and it will be loaded into the analysis chamber, brought to another position, and then the rod will, of course, go back to the parking position. So the software is based on the CAMECA 7F. There have been some improvements, but it is based on the 3 main data reduction system programs: WinCurve for depth profiling and mass spectra data processing, WinImage, which is dedicated to ion imaging data processing, and we have improved the WinIsotope software for isotope ratio data processing. It allows online data reduction during acquisition. So to summarize the ACTINIS key features, so it's a magnetic sector design based on the CAMECA IMS-7F. It's with additional improvements in its design based on the experience from the first generation shielded instrument, the 6FR. It provides high mass resolution, which is, of course, very important because very often there are mass interferences, particularly at high mass, for example, when analyzing actinides and fission product elements. Provides high sensitivity, which is very important in order to be able to detect low concentration levels. Provides depth profiling with excellent depth resolution, element and isotope mapping with down to sub-micrometer lateral resolution. It also allows precise measurement of isotopic ratios thanks to this dedicated detection system with 2 Faraday cups and 1 electron multiplier. As all the CAMECA IMS instruments, it also provides a stigmatic imaging, which is a microscope imaging mode, which allows to very quickly navigate on the sample, and it is very useful for tuning. So there is a specific automated entry load lock. Even though it is motorized, there is possibility of manual control in case of failure. There is a PC automation system with full computer control, with a multitasking system allowing simultaneous data acquisition and data reduction. And it has all advantages of the last generation 7F, remote control, software improvements. So I will now switch to the applications. Let me just check what time is it now. Okay, we still have time. So the benchmark SIMS performance is very critical, and it's very important for studies on irradiated nuclear fuel. One can perform isotopic ratio measurements for characterizing the nuclear reactions occurring during in-core irradiation. It also allows isotopic cartography for investigating the behavior of fission products, and of course, depth profiling measurements for characterizing, for example, fission gas distribution. You can see an example here. It's the data obtained in samples provided by CAMECA. So these images were obtained on cerium oxide, which is a known substitute of uranium dioxide. Scanning ion images were obtained with a field of view of 175 by 175 microns. And for the metric species, cerium, potassium, barium, and lanthanum. The lateral resolution, which is determined by the primary beam size, was about 1 micrometer. So we can see that on the cerium image, we can distinguish the different grains. Different color, in fact, corresponds to different intensity from the different grains due to the different crystallographic orientation, giving slightly different response. And we can see that the impurities, potassium, we can see it is distributed as small particles, whereas the barium and lanthanum, it's on the grain boundary. So it's clearly distributed along the grain boundary. So these results have been published in a paper which describes, for those who are interested in really the dynamic SIMS applications in nuclear science. It's one of the examples presented in the paper. Also in the paper, we have shown depth profiling in the same sample, depth profiling of Xenon, because this sample, this cerium dioxide sample, has been implanted with the Xenon 129 with a high dose, 1 is 16 atoms per centimeter square. And then it has been annealed at high temperature during 4 hours. The depth profiling has been performed using oxygen, impact energy. We use also the electron gun for charge compensation because it was an insulating material. And each profile took about 20 minutes. So we can see here the profiles that have been obtained. It's the same profile, but it's on a log scale on the top and linear scale at the bottom. So it's very interesting because we can see that we have a baseline, which is a very typical depth profile obtained on an implanted sample. But on top of this baseline, we see successive spikes. And in fact, these spikes indicate the presence of gas bubbles that, when they are released, result in an increase of the signal, a very quick increase of the signal. So the gas bubbles are expected to form during the annealing process. And we can very well see them during this SIMS analysis. Another example is the neodymium isotope study in simulated nuclear fuel. So two samples simulating burn-ups of 3 and 8 atom% were obtained by doping non-irradiated uranium dioxide with a known concentration of elements representing fission products. And this is a very nice example showing the very comprehensive analysis that can be performed on radioactive or non-radioactive samples because of the different capabilities of SIMS, both mass spectra, ion mapping, and isotopic ratio. We can see here the mass spectra that has been obtained on the 3 atom% of sample that clearly reveals the complexity of the sample with many mass peaks recorded at different mass units. Here we can see the ion maps for different species, the oxide, uranium oxide, neodymium oxide, barium oxide, and also strontium. And we can, which allows to show that strontium and barium are really localized as precipitates at grain boundaries, whereas neodymium is homogeneous as the matrix species. And here, isotopic measurements have been also performed for the neodymium species. And ratios, of course, are similar for the two samples because it was a natural isotopic abundance. But so it allows to check any variation of isotopic ratio. And of course, after irradiation, the isotopic ratios can be very different from natural. Another example is the helium depth profiling in tungsten film samples. So in nuclear reactors, helium migration, helium trapping will affect the mechanical properties, will affect the structural nuclear materials. So if we want to ensure longevity of these structural nuclear materials, it is very important to understand helium diffusion mechanisms. How does it distribute below the surface? So the goal of the analysis was to evaluate the SIMS depth profiling capabilities when analyzing helium in tungsten. It is known that the helium and all other noble gases, it's not a very favorable case for SIMS. They do not ionize well. So in general, it is not easy to analyze noble gases. But we wanted to really to evaluate the detection limit that could be obtained for helium in these metal samples. So there were 6 tungsten film samples. It was a nanochannel tungsten film samples irradiated with helium ions at several dose values, and some of the samples with annealing. So we have used the conditions that I didn't mention before, but MCS plus technique is one interesting technique for detecting species that do not ionize very well. Instead of analyzing helium alone, we are going to bombard the sample with cesium primary ions and then record the cesium plus helium cluster. And it allows to overcome the low ionization yield of helium, so to guarantee the best sensitivity. Helium measured using cesium helium, it's not that easy. Why? Because you can see here a sketch of what happens when we have a very high intensity peak. There is a peak tail that can go up to another mass. What happens is that when we measure cesium helium, we have a very high intensity cesium peak here, and cesium helium will be there. So there will be a background coming from the cesium peak tail. What we have done, a small trick, was to use medium mass resolving power. So instead of being blue, we switch to red, which means that with high mass resolution, we can have a mass peak which is narrower. And in this case, the background will be reduced for the cesium helium. Still, it's a relatively medium mass resolving power, so we still keep sufficient transmission. We can see here the profiles. This data has also been published recently. And we can see the depth profiles in the different samples with different dose values. There was also a pristine sample with no ion implantation here. Each profile took about 16 minutes. And we could achieve a detection limit about 610 to the 17 atom per centimeter cube, which means about 10 ppm, which is very good for helium, which is a noble gas. There have been 2 runs performed on each sample that show a very good reproducibility as well. So between the 2 runs. And it has also shown that for the higher dose value, in fact, the real dose implanted in the sample was smaller than this value. And also when using annealing, particularly with high temperature, we can also, SIMS could also show that there was a loss of helium inside the sample. So from the CAMECA website, you can have access to the ACTINIS brochure. There is also a nice dynamic SIMS booklet that explains the dynamic SIMS technique. You can also have access to 2 webinars that can be of interest to your applications. One about principles of dynamic SIMS and the other one about the application of dynamic SIMS to the characterization of nuclear materials. So I will conclude here. I am late. So ACTINIS will provide excellent SIMS capabilities for radioactive samples. 2 instruments of first generation were installed in the past worldwide, and 1 ACTINIS is now being installed in CA, France, for replacement of the 6FR. And CAMECA is the only company that designs magnetic sector SIMS for analysis of radioactive samples. Don't miss today, this afternoon, the SCAFIA poster and also the Atom Probe poster as well, if you're interested. And I will stop here. I'd like to thank you for your attention, and we can switch to questions if there are questions. Thank you very much.
Thank you for your speech. There is one question in the Q&A. I don't know if you see it.
Yes, I can see it.
What gases can be utilized for depth profiling?
So the primary ion beam that is used for bombarding the sample there are 2 main types, cesium or oxygen. So for bombarding the samples, you have essentially 2 options. Then for the species that can be analyzed, we can analyze all species of the periodic table. The question is what is the ionization efficiency for those species? There are those who can ionize better than others. In principle, our example of Xenon depth profiling has shown that we can analyze also species that are present as a gas bubble. It would be interesting to further investigate the possibility of SIMS to study other gases. Up to now, there have not been a lot of studies in this field, but it would be of interest. And we are always open to collaboration. So if you have interesting samples that, we can measure it in our CAMECA factory, of course, non-radioactive samples. But it's something of interest for sure.
You have 2 more questions.
Is it possible to have a rotating stage? No, unfortunately not. Not in ACTINIS, I mean, because we really need to have a full security introduction system. We cannot miss the sample inside the SIMS. It will be a disaster, as you can imagine. because it's a radioactive sample. So it is not possible to have a rotating stage in ACTINIS. It's possible on CAMECA 7F, but not in ACTINIS.
And last question I have here, the typical procedure to move the samples from the shipment carrier pig into the ACTINIS and the handling tools that are compatible.
So for now, what has been done in SEA is based on their installation, what they have. They have an hexagonal cell. If you see the 3D view of the ACTINIS, from one of the side there is a connection to a cell from which the sample, there is a tube simply, and the sample is coming from another cell going directly into the glove box. But of course, this is something that may be different from one lab to the other. We would need to see. But in CA, this is how it's happening.
Thank you. I do not have no more question on the Q&A.
So if you have any other questions, I put my email on the last page of the workshop. You can always contact me and I will direct your question. If it's more technical, it will be more for me. If it's more or sales oriented, I will send it to Adrien, which is, as you see there, he's the product sales leader for ACTINIS worldwide. So you can always also, if you have any question, don't hesitate to contact us.
Okay. So thank you all for your participation in this workshop, and good continuation also for the rest of the NUMAT conference.
Goodbye, everyone.
Thank you.
Thank you.